Alright guys, so in this one we're going to take a look at a few more examples that utilize Newton's second law that we looked at in class. So, the first one, a man pushes a 50 kilogram crate across a frictionless surface with a constant force of 100 newtons. So let's go through all the stuff over here on this side first. So the weight of the crate, remember we said that the weight is going to be, the weight is the effect that gravity, the gravitational field has on the mass of an object. So the force of gravity is mg. And so for us, our mass, right, was 50 kilograms. So we have 50 kilograms for our m times our regular 9.81, right, newtons per kilogram for our g. And you'll see right off the bat, right, that the kilograms, this is in the numerator, this kilograms is in the denominator, those cancels, that's a good sign, because I'm looking for a force overall, force of gravity, and I'm just left with newtons here. So the 50 times the 9.81 gets me 491 newtons. So that is the weight of the crate. It's also the force of gravity on the crate. They're the same thing. So then the normal force, just conceptually, if the weight is 491, right? If F of G is the weight pulling downwards, F of G, then the normal force that's pushing back upwards has to exactly balance that out, because the crate's not moving, it's not accelerating vertically at all. So if this is our normal force, right, and F of G is 491, then our normal force also has to be 491. And like I said in class, you might be thinking to yourself, well, these don't have positive, if we're calling both of these positive, that's not quite right, because this one's up and force of gravity is down. Shouldn't force of gravity be negative? You can talk about it that way, and we're not quite there yet, talking about them forces as vectors, but you would be correct to with the concept that they are going in the opposite direction for sure. The net force on the crate, so now we've got to start looking at what's going on horizontally. So I've got the 50 kilogram crate, my normal force going up, force of gravity going down, and then we've got a constant force of 100 newtons. So like the man is pushing, that's an applied force, and it doesn't say what direction, but I'm going to say we're going off towards the right here. So that's an applied force because it's a push or a pull, right? So if the applied force was 100 newtons. So our net force, the vertical, is 0 because the normal force and the force of gravity cancel each other out. There's no friction, so the only thing going on horizontally is our applied 100 newton force. And so the net force, when I add them all up, is 100 newtons. That's an awful box. There we go. So now we want to ask what the crate's acceleration is. So this is a direct application of our second law, right? Acceleration is F net over the mass of the object. The acceleration is the force applied to the object divided by the object's mass. So our F net, right, from the last piece up here is the 100 newtons divided by the 50 kilogram mass that the crate has, and that gives us 2 newtons per kilogram. But remember we said that a newton is a kilogram times meters per second squared. So if I've got kilograms times meters per second squared up here, and I'm dividing by kilograms, then my kilograms cancel, and all I'm left with is the meters per second. So this is indeed 2 meters per second squared, which is an acceleration. That's good. That's units of acceleration. All right, let's take a look at the next one. A horse pulls a 500 kilogram sled with a constant force of 3,000 newtons. So last one, right, was a man pushing. This is a pull instead, slightly different. The force of friction between the sled and the ground is 500 newtons. So another difference. Right now we've got friction going on. So let's look at the free body diagram first. My object is this whole thing on the sled. The whole thing together is my object. So I'm just going to put a dot in the middle of the diagram. Easiest thing to start with is gravity downwards, right? I know there's a force of gravity downwards because it's on a surface. I also know that there's a normal force that directly balances it going upwards. So I can put those two in. Those are the same. The horse is pulling the sled, so like there's a horse over here pulling this way. So there's an applied force, right, F sub A, that is in the positive direction, and it's 3,000 newtons. There's also friction going on that's acting the opposite, and friction always acts the opposite direction of the motion. So now I've got F sub little f, force of friction, and it said it was 500 newtons, and it's in the opposite direction of our applied force, so we're going to call this way negative. So again, right, what's the weight of the sled? That's our F sub g equals mg. Mass here is 500 kilograms times the 9.81 newtons per kilogram. That's going to work out to right around 4,905 newtons for the weight of the sled. And what's the net force on the sled? So F net is going to be all of our forces added up. And really we could do an F net vertically for our y components, for our our forces in our y direction, and we could also do an F net in the x direction, but we can sort of just conceptually right off the bat say the F net vertically is going to be 0 because normal force and gravity cancel out. So really what we're looking at here is the net force in the x direction only. But we would, it's perfectly fine if you just call that F net and kind of skip the conceptual step writing it down of that the y ones are 0. So all the forces in my x direction are the force applied and the force of friction. My force applied was positive 3,000 newtons, and my force of friction was negative 500 newtons. So that works out to positive 2,500 newtons, right? Another bad box. Let's fix that. Positive 2,500 newtons. And since it's positive, it means overall in this direction, that's the net force towards the right, which makes sense. If the horse is pulling the sled must be moving this way. The applied force is overcoming friction since it's moving that way. What's the sled acceleration? So remember, because we have a net force, we must have an acceleration. So again, our second law being applied here, F net over m, gives us our acceleration. My F net we just got was the 2,500 newtons positive over our 500 kilogram mass, right? The sled was 500 kilograms. And that works out to, I can cancel the zeros, 25 divided by 5 is positive 5 meters per second squared for an acceleration. And that's what we've got there. All right, let's take a look at a couple more here. A block is pulled with a force. So now we're looking at objects that are being pulled. The last situations we looked at objects being pulled or pushed just horizontally, right? Perfectly horizontally. Now we're looking at, we could have examples which are actually more realistic of something being pulled with like on a slight angle, so a little bit vertical and a little bit horizontal. So a block is being pulled with a force of 100 newtons, but instead of being pulled perfectly horizontally, like the horse was pulling that sled, it's pulled more at a 30-degree angle. And the applied force can be broken into components, right? A vertical dimension and a horizontal dimension. So our block has a mass of 10 kilograms, and let's look at the components here, right? So in the vertical direction, I've got the gravitational force, I've got the applied, right, there's a component of the applied force that goes upwards. If this, hold on one second, if this arrow, the red one, is the applied force. Then there's a vertical component going on here, which is this black arrow, and I'm just going to draw it in here. And there's also a horizontal component, which I'll highlight here. I don't want to use pink because we've already got pink, but blue is this horizontal component, right? So the vertical is, there's a balance going on here, right? The box is not moving up or down. It's not accelerating up or down. So everything going up must be balancing out everything going down. Now the only thing going down is f of g. So that means that f of g must be equal to the FA and the normal force, right? There's a normal force that's going up because it's on a surface. There's also an applied force, a piece of my applied force that's on an angle is going upwards. So we've got that the force due to gravity equals the normal force plus the applied force, the vertical component of the applied force, right? The y component. So we want to know what the normal force is. If I take a look at, I can rearrange this, right? I can take my Fn, that's going to be equal to the force of gravity minus Fa in the y direction. And actually, let me back up a second. I think there's a little bit clearer way we can look at this. So if I just want to look at what my normal force is, I can start plugging in the numbers that I've got here, right? There's a 50 Newton force going upwards from our component. So I can put in that there. And then the Fn, we don't know right now. We can figure out what the Fg is. So let's take a look at what the Fg is, right? The mass, Fg equals mass times g. So our mass is that 10 kilograms. G is the 9.81 meters per second squared. And so overall we have 98.1 newtons for our Fg. So I'll put that in right here. We want to figure out, I want to show you how I've got this 50, right? So the force applied that's in the y direction, the y component, right, the vertical component of this is going to be the sine, right, using our definitions, the sine of 30 degrees times the magnitude of our overall force, right? And we've been putting that in front, so I'm going to move that over. Put the 100 Newton total applied force in times the sine of 30, and that comes out to 50 newtons. So that's where I'm getting the 50 newtons from right here. And that came from our, right, our definitions that the components in the x direction are going to be the magnitude of the force times the cosine of the angle, and then the y direction is going to be the magnitude times the sine of the angle. So overall here, right, we've got a normal force. I can solve for Fn. 98.1 minus 50 is going to give me 48.1 newtons. So there is a net force in the y direction that we've got going on here. Now in the x direction, the only thing I've got going on is from my applied force, but it's only the x component of the applied force. So the x component of that applied force is the 100 newtons times the cosine of the 30 degrees, and that works out to 86 newtons. Fa in the x direction. So that's what we've got going on in the horizontal dimension and the vertical dimension for this situation. Okay, so let's take a look at these last two examples. So a man pulling a 40 kilogram crate across a frictionless floor with 20 Newton force at a 45-degree angle. So that's pretty much the same situation that we just had with this last example, right? That one was being pulled at a 30-degree angle. This time it's being pulled at a 45. So again, we can split it up into different components. So we have our horizontal component, and I'll call that FA comma X, and then we've got our vertical component, FA comma Y. And in this one and the last one, you may be thinking to yourself, you know, we ended up having a force here overall that we said was in the vertical dimension, but we know that if we're talking about forces, you know, we said that if there's a net force, then there's an acceleration in that direction. But obviously the crate is still sitting on the ground, so what's going on here really? And the answer to that is that if I've got a vertical component of my applied force, then however much my vertical component pulls up, it takes away from the amount that the normal force has to push up. So if I have 10 newtons pulling upwards from my applied force, then my normal force pushes upwards 10 newtons less. And that makes conceptual sense, right? Like if you're pulling up on an object, it's not pushing down into the surface that it's on as much anymore, and so the surface doesn't need to push back as hard to make sure that the object doesn't fall through it, essentially. So if we want to look at the net force on this crate, we can still say that in the vertical direction the net force is 0. It's not accelerating upwards or downwards, it's just sitting on the surface, and it's just being slid sideways by the applied force in the x direction. So first I just need to find what my applied force in the x direction is. So let me do that in the right color here. So FA comma X is going to be the magnitude of our force, which was 20 newtons, times the cosine of the angle, and our angle was 45 degrees. So I'm going to do 20 cosine 45, and that's right around 14.1 newtons. So that's our net force for this situation. The acceleration, again, is just an application of our second law, right? F net over m is the acceleration. So our F net we just found was 14.1 newtons. The mass is 40 kilograms. And that works out to 0.35, right around there, meters per second squared for our acceleration. So now we've got kind of a conceptual question, right? What would happen if the acceleration of the box were pulled at a greater angle? Like if the box were pulled at a greater angle. So if we think, this is another good opportunity for practice thinking about things in the extreme. So if I had a greater angle, like think about 90, just pulling straight upwards, the acceleration, and this was an acceleration horizontally, would be 0. There'd be no component going in this direction if I had, my applied force going directly upwards. There'd be no horizontal component to that force. It's only vertical. So if it was going at a greater angle, I would have 0 acceleration. If it was at a smaller angle, or I guess, so 0 would be the max, right? So at a greater angle we would have less acceleration. You can think about in between where we've got it now at 45 and the extreme case, we would just have less and less of a horizontal component. At a smaller angle, right, if I have my applied force going the complete horizontal direction, then I've got all of it going in the x direction. It's all just an x component. So that increases our acceleration, right? As I bring this arrow down lower and lower, my x component gets bigger and bigger until it makes up my entire applied force. So then we have more acceleration in that situation. So our last example, right? instead of a pull, now we're looking at a push. A girl pushes a 30 kilogram lawnmower with a force of 50 newtons at an angle of 60 degrees below the horizontal. So that angle is right here, below the horizontal, 60 degrees. And she's pushing the lawnmower with a 15 Newton force. And we want to know what the acceleration of the lawnmower is. So, right, we're going to want to plug in an F net over M. But we know what the M is, 30 kilograms, but we need an F net first. So, again, vertically, the components are going to cancel out. Now, it's kind of the opposite situation here. We've got like more push downwards into the surface, right? A component, and I'll draw it right here. There's a component of my applied force pushing downwards, Fa comma y, and that's pushing into the surface along with gravity. So now I've got more of a push on the surface, but the normal force just grows bigger to balance that out. So still vertically, we've got net zero. And so I just want to find the horizontal component, the Fa comma x, for our F net. Now, let's look at how to do that. F net, Fa comma x. And now we have to be careful with the angles here, right? So the 60 was for outside the triangle here. Inside this triangle, as I've drawn it, this angle would be 30 degrees. And the Fx component is not the adjacent angle anymore, right? Normally we would do cosine here because cosine goes along with the CAH in our SOHCAHTOA, right? So the adjacent over the hypotenuse, but now it's the opposite side. So we actually need to do sine to get the x component when we've got this applied force going downwards below the horizontal. So I've got the 15 Newton magnitude, and then I need to do sine of 30 degrees, because that's the angle in my triangle there. And that works out to, let's see, right around 13 newtons for our net force. And now we want to plug that back into our original relationship that we said we wanted to use, our second law relationship, F net over M. So the acceleration is going to be the 13 newtons over the mass, 30 kilograms. And that's going to work out to 13 divided by 30, right around 0.43 meters per second squared. And the last thing to finish up here is another conceptual question. What could she do to maximize her acceleration? So instead of pushing down, like she's wasting a lot of her push, just pushing down into the ground here, right? So she's pushing down, but it's just balanced, it's just making the normal force bigger. The ground's just pushing back and kind of like she's wasting all that push. So what she could do is decrease the angle that she's pushing at, so she's pushing more horizontally. And really she could maximize it if she was pushing directly horizontally. So to maximize her acceleration, she could push, we could say 0 degrees from the horizontal. Or you can think about that as, directly horizontally. That's it for this video, guys. Thanks for watching, and I hope it was helpful. See you in class.